Hello, Assalamu alaikum. Welcome to the lecture number 8 of the series of designing and implementation of RISC-V pipeline code. In the previous lecture, we have designed the top architecture of the pipeline code by integrating all the individual modules which have designed previously. During the simulation part of that lecture, we have came to know that some of the instructions were not getting executed properly because I mentioned that there is because we have encountered one of the hazards in the pipeline architecture, which we are going to talk today. So the hazard which I have mentioned there, it was one of the data hazard which we have encountered in our previous lecture. So today we are going to see that how which type of hazards are available in the pipeline architecture and how we are going to solve them and how the data hazards can be solved with multiple approaches and which approach we are going to use in our this our series. So today we are just going to talk about the hazards. There will be no implementation part of it. So we're going to just cover the theory part of it, and then in the next lecture we are going to implement that solution, and we will see the result after simulating that top architecture again. So without any delay, let's start with our theory. So today we are just going to talk about initially about the pipeline hazards. So there are two type of pipeline hazards which are going to be we occur in our designs. Number one is a structural hazard, and the second one is a data hazard. As mentioned here, you can see that the structural hazard is the hazard of the hardware. Like you have designed a pipeline architecture or some of the hardware which does not support a particular hardware functionality. Like you have design an ALU which only supports addition, subtraction, and some of the basic arithmetic and logical operations. But if I want to perform an operation of a divide, if I want to perform a divide operation, definitely that cannot be done in a single cycle because the hardware of the division is very effective and cost effective. It's highly expensive and you cannot use it in a single cycle. So there we have a restriction that our execution cannot be performed in a single cycle. Maybe the division operation may take up to multiple cycles. It can take 4 to 5 cycles, or depending upon your algorithm you have implemented, it can take up to 34 to 50 cycles as well. So this is one of the structural hazard we have encountered, that okay, the hardware is not supporting the execution in a single cycle, so definitely you cannot get the answer of a particular part or particular cycle in a single way, in a single clock cycle. And the second structural hazard, which we can talk about, that initiating only a single memory for a whole architecture pipeline. As we have seen that in implementation, I have mentioned two different memories. One is for instruction memory and one is the data memory. Just suppose if I have just used a single memory, which can only have a single read write port. So either I can fetch the instruction or I can read or write my data. But in the pipeline, we have seen that we have doing that after many of the instructions, we see that all of our pipeline stages get occupied with each individual instructions. So at every portion of the cycle or pipeline, we are doing some work. Either we are fetching the instruction from the memory or just we are performing some memory operation, read and write of the data. So suppose if I have just a single memory, so either I can fetch the instruction or either I can write or read data. So this is also one of the structural hazards, which is a limitation in our pipeline architecture. That's why we mentioned two different memories. One is separate for the instruction and one is separate for the data memory, so that we don't encounter such hazards. Now come we have the second type of hazard, which is known as the data hazard. Data hazard is basically the hazard which occurred because of the data. You can say that, as mentioned here, the data to be executed is not available. We have seen in our previous simulation that when the third instruction of addition was going perform, as the data decoded or fetched from the register file was both X. It means that the updated data was not currently available at that time of the execution, due to which my data hazard was occurring in our previous simulations. So may occur the reasons the data hazard may occur, that definitely you are running back-to-back instructions, one of the possible cases which we have encountered. And the second may be the possible case is that when you have stalled the pipeline. Okay, stalling is one of the concept that when if you are performing a multi-cycle operation and you need to stall your pipeline, that you have to wait. Okay, let's wait until my previous operation gets successfully completed, and then we are going to move forward. So stalling comes from there. So how we can solve the data hazard? The one of the basic or you can say the optimized solution of the solving the data hazard is by using the forwarding or bypassing technique. What is this techniques is and how we are going to implement, we are going to look into the further. So just look at this slide. You can get an overview of how the data hazard in pipelining is occurring. Okay, I have just mentioned this series of code here. That first we are having an add instruction in which the result is to be updated into the S8 registers. Yani कि S4 values of S4 and S5 will definitely going to get add, and the result will be updated into the S8 register. But after that, you have a subtraction register which is using the value of S8 register. As you can see that the pipelining, the write back stages of the fifth stage of the pipeline. So after the execution, I have to wait multiple cycles at until my register get updated. So the currently the subtraction instruction, which will be the decoding part, which getting the data of asset will be the previous value which I have stored somewhere else in the program. So it will not be an updated value. So this is one of the data hazard we have occurred, that we are using the previous value, not the updated value for our simulations. Like suppose you are doing some calculation and you want the updated value to be used in our future calculation, but as you are using the pipeline architecture, so the value is not get updated and you are still using the previous value. So maybe your calculation is maybe not get corrected and you may encounter lots of error in your calculation. So this is also one of the crucial point when you are performing some very control applications on your processors or pipeline architecture. So you don't want such hazard to be occur, which just manipulate your values and your data get corrupted. So this is the hazard occurring right after the execution state. That right, I'm here you can see that my value is getting updated in the fifth cycle, but the second instruction subtraction is getting decoded into the third cycle, which is way too uh, early than before my write back of the register. Similarly, if I have the third instruction, so here the data hazard occur at the decode stage, from write back stage to the decode stage, that I just not get the value correctly from my decode register. The second hazard which we have encountered is into the third instruction, that you can again see that the OR instruction is again using the asset value. As you can see from the diagram, the arrow shows that the register have not been updated yet, but I want to use that instruction into my third instruction decode part. So again, the third instruction, the register will get the value of asset will be the previous, as my values is not still not updated. So here you can see that I have been using two previous value in two of my calculations of X8 register. So definitely they are going to affect my calculations very badly. And the third error you can see that we can encounter during the third instruction, which are going executing the AND instruction, which is also using an asset data value. Again, you can see that either at one time I'm writing the instruction and at the same cycle I'm also decoding the instruction. So it cannot be happen simultaneously. So here you can see that the register write back and the register fetching will cannot be happen in the same cycle, because most of the time we just write the value at the positive edge of the clock cycle of the register file. So definitely it will going to wait for the positive edge until it get right into the register and get updated. And at the same time, if I am get reading, if I have not implemented any bypassing logic in my register file, then the value I'm getting to read will be the previous value. So you can see that all of these three instructions are just using the previous value of S8, because it is still not updated into my asset register due to my pipeline architecture. So that is why these are the data hazards which we are facing in our previous simulation as well, that when we have used two ADA instruction for updating the X5 and X6 register, and when we use into the third register for addition, so both the values were not get updated till yet, and then why we are getting X on both of the values, and our value getting saved into the X7 is also an don't care value. So this is the, I guess, basic overview of how the data hazard occurs. You can see from the code as well that this also known as a data dependency, that my code has a data dependency of the previous instruction, that my next instruction is dependent on my previous instruction. So you can see here that my subtraction instruction is dependent on my add instruction answer. Similarly, my OR instruction is dependent on my add instruction answer. And the same way, the AND instruction is also dependent on the add instruction answer. So until I don't get the correct value of this answer saved into the register, all of these operations or instruction will get the corrupted value of my register, which will going to affect my calculations. So this is the data hazard which we have occur in our pipelining architecture. So there are two possible solutions as mentioned to solve these hazards. Number one, the solution we provide is number one, we can solve the data hazard by using the knobs. Definitely knobs is the some type of instruction which is used as a delay. If you are very much familiar with the embedded side of the coding, whenever you use some embedded, you provide some delay that you want to wait for a few seconds and then start the execution of some operation. So this is happen in the same way that you are adding some knobs into your instruction memory instruction program. So you have to wait, or you can say just you are stalling your pipeline for that you are nothing not performing any operation on your architecture, and you are just wasting your few cycles until your operation gets successful, previous instruction gets successfully write back, and then you use the new instruction for it. So this is the concept of the knobs. And the second solution which I mentioned already, that is the most using optimized solution that we use introduce the forwarding or bypassing technique into our data path. So the first solution, as you can see here, that we are included two knobs in our instruction, right? This is the I mentioned taking the same program. Previously, you can see that after the add instruction, I directly have my subtraction instruction and then or and. But here, what we have done, that we have introduced two knob instruction between add and subtract, and we have I'm mentioning that I'm waiting for two clock cycles, or you can say I'm providing a two clock cycle delay to my pipeline architecture to wait and not do anything, and then again fetch the new instruction and start its execution. So in this way, what happened that my registers subtraction instruction, that you can see that S8 is getting right back to the fifth cycle, and the value is also getting updated on uh, uh, the subtraction instruction is getting the corrected value which I write into the S8 register. So you can see that these two are the NOP instructions have been, there is no operation have been performed my whole pipeline. Neither my instruction is getting fetched, but there is no decoding happening, no execution, no data memory, no write back. So these two instructions acting as in delay, which provide a two cycle delay in my pipelining, so that the decoding part of my next instruction and the write backing part of my first instruction is happening in a simultaneously at a simultaneous time. So this reduced my data hazard, and afterward definitely my OR instruction and AND instruction will going to get the correct data values of S8, so there is no data dependency is occurring at those instructions. But again, let's take an example. What happened if my subtraction in data register, which is an S2, is all getting used in my OR instruction again? So there is again data dependency occurring. So what do I have to include two knobs again? And if this happening continuously, so how many knobs I am going to implement in my architecture? So this is not optimal way, optimized solution. This will going to introduce latency in my pipeline processor performance, due to which my performance of the, or you can say the throughput of my processor will going to be very much low, which is not a desirable attribute of our design. So that's why this approach is not very much appreciated to be used. Uh, so it is just a basic concept. You can use it as well, but if the cases of the data hazards is very rare in your program, but eventually when the compiler compile the course, it doesn't keep such things in mind that he have to provide this knob and all of things. So you have to manually code these things. So definitely is not an optimal solution for that. So because we want our compiler to generate a code which can be work around on any of the our hardware, rather than providing him some constraints to the compiler that if you have given some data dependencies, you have to introduce this much of NOP instructions. So that is not an optimal, that you have to go and change the make your custom compiler as well. So this is the most optimal solution we are going to talk, is the using of forwarding or bypassing technique. Here what I do, what we do here, that as we know that the answer of my register ALU have been flopped from one cycle to another. Definitely when we are designing the pipeline register, we have seen that the ALU result was the output of my execution stage, but also of the input of my memory stage, and was also an output from my memory stage to an input towards my write back stage. So I can say that my result was available of into all the cycles after the execution cycle. the result was available in the execution cycle as well. My ALU result was available in the memory cycle as well, and my ALU result was available in my write back cycle as well. So why not use that result and just use it as it is, the updated value towards the next calculation. So this is the concept of forwarding or bypassing, that I'm bypassing my stages and just providing the updated value. I'm not waiting for my register to get updated at the write back stage. It will be going to be happen in its what you can say, in its predefined stage, but before that I'm just bypassing my data to new other stages so that they can use my updated data rather than using my previous data. So this will reduce my chances of error occurring in my calculation, so that my data will not be going to get corrupted. So what we have do that I have forwarding or bypass, you can say that forwarded my answer from my memory stage towards the execution stage of my next instruction. So you can see the arrow showing that my data of S8 was just forwarded towards the previous stage of my execute. Right, so definitely there is some hardware will going to be involved in it, which will be controlling this. That's you can maybe saying, okay, how can I map just a single wire to the ALU input port? Definitely the value will be coming from the decode as well. So definitely some hardware going to in, but here is just the basic concept of it, that how what we are going to do, that we are just going to provide the answer from memory state to the execution stage. This will reduce our one of the data hazard which we are facing in the subtraction instruction. In the same way, if we provide the answer from our write back stage to the execution stage of our third instruction. So this will also reduce the data hazard which were occurring in all instruction, because from here we were getting the previous value, but when we use the provided the updated or bypass the value, so the register value get updated in our second operand. So definitely we are going right now we are using the updated value in the execution rather than using the previous value which was stored in any of the previous instruction execution. And similarly, what we have done that we have forwarded the register right back to the read operation here in the write back stage. So here we have three forwarding parts, one from data memory towards the execution stage and from the write back stage towards the execution stage. Definitely, I'm not forwarding it towards the decode stage, because definitely you can fetch the data at the decode stage. All we have to do is to perform the execution correctly. So all the forwarding logic will be applied to the execution stage, not to the forwarding decode stage, not to the data memory stage, not to other write back stage. All we have to do is just we have to forward the data from different data memory and write back stage and provide it into the execution stage of our architecture diagram implementation. So I hope this makes the concept very much clear to you. So let's see that after implementing the forwarding logic, what changes are going to be occur in our pipeline architecture. So here is the top updated pipeline architecture which we are going to implement in our next lectures. As you can see that there is no such change in my fetch. It is similarly as it's shown here. Same goes with the data decode stage, but here you can see that some of the signals have been used. Uh, uh, Extra signals have been carried out to use in our forwarding logic. Similarly, there is no such changes in our execute cycle, but just we have introduced two more mux, 3 by mux, which are getting controlled by my hazard units, which is responsible to control the data hazard. And this is how my forwarding is getting executed. That I've implemented a 3 by mux one on the input port of my ALU source A and source B. So the operands of my ALU is getting updated, or you can say is getting manipulated by my logic of that hazard units. So it may get updated, get the value from the decode stage, which is getting actually the correct data, or it can get bypassed from the memory stage, or it can get the data bypassed from the write back stage. So this is how we achieve our forwarding logic here by using the control signal, which is definitely going to generate by our hazard, which is going to check for some conditions that either the register values or register number are exactly the same or not. On that basis, my control signal will be generated, which is going to uh, control the mux input and output towards the ALU. And same there is no such change in my memory cycle, and same there is no such change in my write back. Only the some of the signals are getting used as an output and are like you can see that the ALU result have been used as a forward back wire towards the execute cycle, and same the write back happen towards my write back stage as well. And you can see that some of the signals of our destination M was used from memory cycle towards the hazard unit, and same as it is used from my write back unit. So I can perform an condition that it's going to check that the current RS1 and RS2D is either exactly same towards the RDM and RDW or not. If either of them get selected, condition get true, so it will going to select the value accordingly. So definitely these details will going to be we are going to see in further in our implementation lecture. So not going much into the detail. So this is the top architecture which we are going to implement in our next few lectures. So I hope this make the concept of pipeline data hazard very much clear, that what type of hazards we are facing in our pipeline architecture and how we are going to solve the data hazard by using two approaches. One is the knob and second is the forwarding or bypassing. As knob is not an optimal solution, so we are going to implement our forwarding and bypassing logic, which have which yield us to the updated top pipeline architecture. So I hope this makes the concept very much clear. So stay tuned for the next video in which we are going to implement this architecture. So take care and Allah Hafiz.